Hey everybody, this one is about hypothesis testing in action. Specifically this week we're focusing on one sample Z and T tests. But we're really in the inferential statistics part of the class. So we're no longer just describing a data set, we're now trying to take that data set and infer to another population or to the same population. There's different ways to do this, but we're going to be focusing on the difference area. And as you can see, there are so many different types of difference testing. This is why people hate statistics. We are focusing on one sample and Z and T for the week. We're not going to get to test or proportion. In a few weeks, we'll get to two sample tests, focusing on independent t-tests, which has two options, and dependent t-test, which is our pre-post. There's also ways to do this with proportions. This class does not talk about 3 or more groups. This is ANOVA, and we'll get to that if you take intermediate statistics. Now, before I go too much further, I want to talk about the logic behind all of these hypothesis tests. So every test that you do from here on out is going to have 6 parts. Number 1 is setting hypotheses. This is the most important part because we're not qualitative. So in qualitative, we're just describing everything that we see and we're making just some assumptions. That's not what this is. We have a hypothesis and we see, does the data support that or not? 2 options, yes or no. If it does support it, we say something about that. If it doesn't support it, we say something about that. But we have hypotheses and that's what we're testing. So we have to have hypotheses. Then we pick a test. As you just saw, that's the hardest part of this, is picking the right test. Then we calculate the test. We change that to a p-value. And then we compare P and alpha. Number 6 is the most important part of this whole course, and that is, what does it mean? So we reject the null, okay? We don't reject the null, okay? What does that mean? And what does that mean in practice? Who is different? How are they different? Are they higher? Are they lower? What does that mean for your practice? That's what we're going to be focusing on. I'll get you through the calculations and picking the tests, but really be thinking about how we assign meaning to all of these findings. It's not just getting the correct answer. All right, so let's look at some examples. So what we're trying to figure out is our sample different from a population? So when we're thinking about t-tests in 2 groups, those are the 2 groups that we're really testing, sample and population. And we're either going to use a Z or a T, which we'll come back to. This can be all kinds of different things. If we did a reading intervention, we want to see if that group is higher than our non-reading intervention to see if it worked or not. Medical interventions do this all the time. We can do the same thing in business with advertising. It doesn't matter, but there is something about this sample that we want to see, are they significantly different than the population? And there's usually something associated with it. It shouldn't be obvious. You're not comparing your GT kids to the general population and are like, oh, I teach kids that are higher. That's a duh moment. So there has to be something about this group that you want to see, are they significantly different than the standard population? So let's go through this a little bit. If I'm thinking about homeschool students and I notice that I think my kids are scoring higher than the public school students, that's my observation. I could create a whole research question around that. Are they significantly different would be my research question. So the null hypothesis would be that the mu, this symbol right here, which is the public school student. So I'm assuming that the public school is the population. And so the population mean is equal to the homeschool mean. That right there says that there's no difference between the population and the sample. They're the exact same. My alternative hypothesis, I actually have 3 different options. You're going to choose one. So I could just say they're not equal, meaning I don't care who is higher, who is lower. I just think that they are significantly different groups. That would be a non-directional and 2-tailed. If I think that the homeschool is higher or the homeschool is lower, those are going to be directional hypotheses. Now, according to my observation and my research question, I'm saying that I think homeschoolers are scoring higher, so I'm actually going to have a directional hypothesis here. It's going to be a one-tailed. if my homeschoolers end up scoring significantly lower than my population, than public schools, I'm not interested in that. That's not helpful. That didn't answer my question. My question is, are they higher? So that gets us through step 1. We have formulated our hypotheses. Number 2, we have to decide on a test statistic. This is either a Z or a T in this case, but we'll come back to that in a minute. Then I'm going to calculate my Z or T tests with the data that I have. I'm going to find the probability that is associated with this. This is where we could go back to those really awful t-test and z-test values. You remember from last week, all of those awful charts, and try to find them. Or we can use a really quick online calculator, which is the way that we're going to do. We're not looking at critical values in this class. It's the same concept, but p-values need to be reported anyway, and they are way faster. So that's what we're going to do. And the probability is your p-value. And then we have to decide if it's a rejection or if it's not a rejection. And this is where we're comparing our alpha, which is our critical level, 95%, 99%, and our p-value. And remember that these tests operate under the assumption that the null hypothesis is true. So if we can provide evidence that this is not true, or that the chance of this is being true is very small, that's when we get to actually reject the idea that everything is the same in support of the idea that there is a significant difference. So here's your rules. If your p-value is smaller than alpha, you have a significant result. So if you found a p-value of 0.02 compared to your alpha of 0.05 at 95% confidence, then you get to reject the null to support the alternative hypotheses. What that means is that there's evidence that the sample is significantly different than that population. But if our p-value is larger than alpha, this is not a significant result. So we failed to reject the null. We don't accept the null, we just fail to reject it because we're never confident of anything fully. And what that means is that there's no evidence to support that there is a difference. It's likely that the mean differences, those values that we found for your sample mean and your population mean, are just due to chance, and it's not a real difference within the whole population. Here's just a quick note, because many of you are not used to looking at decimals, and this will trip you up. If we're looking between 0 and 1 is way, way, way over here off the screen, 0.05 is very, very, very small, and we only have this amount to reject the null hypotheses. So watch the zeros and watch where they are. 0.1 is quite large, 0.01 is quite small. So this is bigger than this, in which case I would fail to reject a 0.1 if I'm comparing to either one of these. So keep an eye on your decimal. If you need to get out a number line and just check to see, do it. There is no shame in that if you have not been in a math class for a long time.